we have some extra condition. We want the one form, the restriction of the one form to this submanifold to be 0. Right? So the one form vanishes at this link. So this is a working definition. So there's a more general definition in a general setting. So instead of R3, you can replace it with any 3-dimensional contact space, and then you have a similar kind of definition. Okay, so for the scope of this presentation, let's just use this. And then two Lagrangian links are said to be Lagrangian isotopic if there exists an isotopy from one to the other, such that it's slightly stronger than being topologically isotopic. Okay? So there are links that are topologic, there are Lagrangian links that are isotopic as topological links, but not as Lagrangian links. So Lagrangian isotopy is strictly stronger. So things that are invariant under Lagrangian isotopies are called Lagrangian invariants. So invariant is put an adjective in front of it, Lagrangian link invariants. So let's see an example. So actually prepare an example. So this is, so I hope you can also see this screen. Okay, so I have the formula here. So you can check that this satisfies the vanishing condition on the one form. And it looks like this. It's a knot. And so there are two particular angles I want you to look at it. One is this one. So if you project it to the XY plane, it looks like a number 8. Looks like this. So remember this shape. And then if you project it to the XZ plane, it looks like this. Okay. So it looks like just a circle. Looks like this. So these two shapes will appear, these two kind of shapes will appear throughout the talk. And so we'll go back to the presentation. Okay, so these two are known as front projection and Lagrangian projection. So the front projection is projection from XYZ to XZ, and Lagrangian projection projecting from XYZ to XY. Okay, and the reason it's called Lagrangian because the image of, so the XY R2 is itself a symplectic space, and the image of this projection is actually going to be a Lagrangian inside the symplectic R2. Okay, all right. So next I want to talk about ripcords. So double points in the Lagrangian projection are called ripcords. Okay, so in other words, the ripcords are points that are pair points that have the same x and y coordinates. Okay? And so let me just use a knot case to depict what the ripcords look like. So in the Lagrangian projection, there's a double point, right? So you look at the projection and see where the crossing is. So that's the ripcord. On the other hand, if you look at the front projection, it's actually a chord pointing from one point to another point, and these 2 points will have the same xy coordinate. And the y coordinate, you can see the y coordinates by taking the derivative. Okay, so basically it's a pair of points with the same x coordinate and parallel tangent lines. Okay, so that's how you see ripcords.
Sorry, Matt. So for this choice of dimensions, projection of any one-dimensional to symplectic two-dimensional is Lagrangian, right? So
yeah, sure.
So it doesn't say anything except the image has symplectic form, right?
Yes, so there are higher dimensional generalization of these projections. You're right. Yeah. So here it's a special case and seems it's not as interesting as the higher dimensional ones. I agree. All right. So next, let me talk about the characteristics of the two projections. So let's first talk about front projection. So in the front projection, you can actually recover. So looking at the image of the projection, you can actually recover the pre-image by taking the y coordinate to be the slope, right? Because because of the vanishing one form condition. So dz minus y dx is 0. Therefore, y is equal to dx, d0 dx. So you can do this to compute the y coordinate. Okay. And consequently, we're not allowed to have vertical tangent lines. So if you want to actually go back, right, in this kind of U shape, it's not allowed. So instead, you have cusps. So you saw from an earlier a knot example that there are two cusps at the two ends. So that's why you have cusps. And there's also no need to specify the over or under strand, right? So whenever you have a crossing, it's always this. It's always the one looks like this. Why is that? Because this one has negative slope and this one has positive slope, and the positive slope should be further deeper down inside the blackboard, because the y-axis, if you draw the x and the z-axis, the y-axis points into the blackboard. So the bigger y would be deeper in the blackboard. Okay. And next, for any immersed differentiable curves, except at the cuts or crossings, with no vertical tangent in front projection, is always some sort of Lagrangian links. So whenever you draw a shape with this kind of vertical tangent line and it's smooth enough, and you allow to have crossings and stuff and cusps, then you get a front projection. Okay. On the other hand, Lagrangian projection they have stricter requirements. So for example, integrating the one form ydx along the image of any link component is always 0. Okay. And by Green's theorem, this imposes some sort of area condition on the Lagrangian projection, because because you're computing the area enclosed by the curve, so the signed area should sum to 0. Okay, so therefore it's hard to draw a Lagrangian projection. It's easy to draw front projection. It's harder to draw Lagrangian projection. However, if you want to see ripcords, it's easier to see ripcords in the Lagrangian projection, harder to see in front projection, because front projection, you have to actually find same x with this parallel tangent. And depending on your drawing skill, it sometimes could be difficult. So next, let me talk about Legendrian randomizer moves. Right. So we learned in topology that isotopic links one to another using randomizer moves. So there's a Legendrian version of that. So there are also 3 randomizer moves. This is the randomizer 1, which takes a straight line and make this loop inside. Okay, and then so I'm drawing them in front projection, as you can see from the cusps. Okay, and next, if you have a cusp and then you have another strand, and the slope, if the slope is either bigger than both the strands in the cusp or smaller than both strands in the cusp, then you can move them in and out. Okay, no problem with that. And randomizer 3 is the same as before, so you just pull the string down. Okay, so that's randomizer 3. All right. So before I dive deeper into the story, let me just give like 2 classical numerical invariants. So the one is the Thurston Bedinger number, and then the other is the rotation number. Okay, so here for convenience, I really want lambda to be oriented. So you put the orientation on each component of the link. Okay, and let me use the front projection to compute. So you can actually do it using Lagrangian projection as well, but for convenience, let's use front projection. So first, you would compute the right of the link by taking this difference. Okay, and then we also call a cusp a down cusp if it's pointing down. So if it's going this way or this way, so that's a down cusp. And on the other hand, if it's going up, then it's called an up cusp. Okay, so the Thurston Bedinger number is equal to the right of the link minus half of the number of cusps. So cusps, it's always, number of cusps is always an even number, so you take half of them. And the rotation number is half of the difference between down cusp and up cusp. Okay, so for example, if you compute the Thurston Bedinger number of the Lagrangian link, Lagrangian or not, you will see that the Thurston Bedinger number is -1, and the rotation number is 0. Okay, so this is actually, so there are actually many Lagrangian links that are topologically that are not, and this one has the biggest Thurston Bedinger number. So it's sometimes also referred to as the maximum TB or not. So next section, I will talk about the Chekhov-Ilya-Ashburn DGA and augmentation variety. So first, let's talk about some history of the Chekhov-Ilya-Ashburn DGA. The Chekhov-Ilya-Ashburn DGA was first introduced by Chekhov as an algebraic invariant, and the original version was done in characteristic 2. And then Ekholm, Ng, and Sobolov gave an interpretation of this DGA using symplectization of the contact R3. right? So become R4, and they also define a characteristic 0 version of the GA and with decoration on it. Okay? And then later, Ekholm, Hunter, and Kalman, they constructed from the cobordism category of Lagrangian links to the category of DGAs, and then mapping the link to the Chekhov-Dili-Ashford DGA. However, in their paper, they did the construction in with this plane curve, plane links. So in our project, we actually enhanced the EHK functor to characteristic 0 together with decoration. So we have to include the decoration in it, and it's a very important part of our story. All right. So let me try to give the definition of the Chekhov-Dili-Ashford DGA. So let's first let lambda be an oriented Lagrangian link, and each component has rotation number 0. Okay? And you need to first fix a mass of potential. So what is the mass of potential? So mass of potential is basically a value function. So you look at your link, you delete the points that map to cusps under the front projection. So you have pieces of segments, and then you assign number to each piece, such that at each cusp, the upper strand is always 1 bigger than the lower strand. Okay, so that's the mass of potential. Okay, but in order to compute the DGA, it's easier to compute inside Lagrangian projection. So Legendrian gave the front projection into some sort of static picture of a Lagrangian projection. So the way you do this is to turn left cusp into just a rounded cusp into some sort of small loop, and then turning each crossing into, so you just remember the overstrand, the understrand in the crossing. Because in Lagrangian projection, you really have to specify which one is over and under. Right? You only, it's important piece of data. And why static picture? Because I mentioned that for Lagrangian projection, you really need to, for true Lagrangian projection, you really need to have this equal area condition. So by just doing does not, it always breaks this equal area condition. But there's always a way to save it, improve. But for convenience, not keep drawing these big loops on the right-hand side of our link, because we take up too much. Draw this kind of schematic picture from now on, and just remember there's always a way to make it precise if you want to do it precisely. Okay, so we also decorate the Lagrangian projection. So now I have Lagrangian projection of my link, and we decorate it with mark points away from crossings, such that each link component has at least one lift of such a mark point. So the mark point will be drawn away from the crossing, and when you lift all of them in back to the R3 to link in R3, you make sure that each component has at least one mark point in it. Okay, so we find this set of formal variables t to be ti plus minus 1. So now let's construct the Chekhov-Dili-Ashford. Let's first define the algebra, and then define the grading, and define the differential. So differential is the hardest part, so we save it to the end. Okay, so the algebra is actually quite easy. So you take the set of ripcords in the Lagrangian projection. So those are the crossings, double points. And you also remember this formal variables on the decoration, so ti. So each decoration has one formal variable, and then you're allowed to invert the formal variable as well. So you have the ti inverse. And then the Chekhov-Dili-Ashford DGA as an algebra is freely generated by this formal variables over z with the condition that ti times ti inverse is 1. Okay, so it's quite free. Okay, for the degree, for the grading, each mark point each formal variable has degree 0. Okay, and then for a ripcord, right? So for each ripcord, it's a crossing inside the Lagrangian projection. So if you look at the real ripcord, it's actually there are two strands, right? And in particular, one has higher z value and one has a lower z value. So we'll call the higher one called the overstrand and the lower one called the understrand. So the degree is computed as the difference of the mass of potential on the overstrand minus the understrand, and then plus the Morse index at, so you first take the difference, the height function, and you compute the Morse index at this critical point, right? So this ripcord can always make it into a critical point of the height function. And so the Morse index is basically either 1 or 0, right? So it's a local max, it's 1. If it's local min, it's 0, right? So if you do Ing's resolution, it's always a local max. So this is always 1. And then at the end, you subtract 1. Okay? And then the differential is harder to define. So first, let me square 0. And differential on formal variable ti is 0. So for the ripcord, however, it's harder to compute. So you have to actually do some sort of inverse disk counting. Okay? So what do I mean by that? So first, for each crossing in the Lagrange projection, you have to label the rip signs and the orientation signs. So there are two packages of data. Rip signs only depends on the overstrand and understrand, so the position of the overstrand and understrand, and the orientation sign depends on orientation. Okay? And so now for each, so fix a ripcord B first. So that's the one that you want to compute the partial. And then for any tuple of ripcords, so C1 to Cn, so let this M be semicolon C be the set of inverse disks with boundary partial U inside the Lagrangian projection, and also cusps of this following form. So you allow to have one positive rip side at rip sign at the B, and then all the rest of the cusps, they should all be at the minus corner of the picture. Okay, and then we define sine U to be the product of orientation sign. So this is important. You're only taking orientation sign when you compute the sign of the disk. So product of orientation signs at cusps of partial U. So this minus sign, they do not contribute to the sign of the disk, right? These are only signs for making sure that the corner is at the minus quadrant. Right? When you compute sign, you should look at orientation sign. Okay, and then you define WU to be the word obtained from the boundary. So you start at B, and then you just go counterclockwise around your disk, and then you just recall all the labelings. So let me do an example. So this is formula. So partial B is equal to sum over all tuples, sum over any disk inside this moduli space, and then the terms you're summing is sine U times the WU. Okay. So let me give an example. So here's an example. So decorations on the boundary of the disk. Suppose when the disk is passing those mark points along the way, and also I shaded one of the corners because, so suppose this one is inside this shaded region orientation sign. So you have that. Then when you compute this term, you will get the following. So you start at B, so you go counterclockwise. So first you go to C, so so it be C1, and then so this red arrow is indicating the orientation of the link at this strand. Okay, so the orientation is going this way. Then this orientation is opposite to the link orientation. So you pick up T1 inverse if you have opposite orientations. And then next you have C2, and then you have C3. And the next one, you're going along with the link orientation. So now you pick up a C2, and then you have C4, and then you have C5, and then back to B. Okay, so this is WU. And then the minus sign, because one of the corners is shaded. So if there are odd number of corners shaded, then it's a minus sign. If there are even number of corners shaded, then it's a plus sign. Okay, so that's how you compute the term. All right, so let's actually do an example. So let's consider this Lagrangian link. Okay, so first I assign the mass of potential. I assign the 1 to the top part and then 0 to the bottom 2 strands. Okay, so you see that at each cusp, the top is always 1 bigger than the bottom. Okay, and then I do Ing's resolution to this picture. So I turn the left cuts into a smooth corner, a smooth arc, and the right cuts into some sort of loop. So you have that, okay, and I decorate it. So I put one mark point at here and one mark point here, okay, and so let me label all the ripcords in this picture. So you have 3 here, B1, B2, B3, and then there are 2 here, A1 and A2. So those are the ripcords. Okay. So as an algebra, so A is freely generated by TI plus minus 1, BI and AI. And then the grading, so TI and BI of degree 0, and the AI is of degree 1. Okay. So if you follow the recipe of computing the grading, this is what you get. Okay, so since the multiplication respect grading, right? So the whole algebra is actually concentrated in the non-negative degrees. So when you take partial of Ti and Bi, they automatically 0 because right, the partial is of degree minus 1. So there's nothing further down that you can go. So the partial is 0. However, the partial A is more difficult to compute. So in order to compute partial A, so let me actually first label all the quadrants. So actually, I'm just keeping the plus label. So the unlabeled quadrant, they are minus signs. Okay, so it keeps the notation simple. So you have so these are the positive quadrants, and the unlabeled quadrants are minus. Okay, and then the orientation sign will look like the following. So only the B's have orientation shadows. So have shadows at these quadrants. Okay, so let's first compute partial A. So the first disk you see is this blue disk in the picture. So this is a disk with a plus corner at A1. So, and if you look at the orientation, if you go counterclockwise, and the link orientation is clockwise, so they're opposite. So you pick up the A1 inverse. Next disk you can see is this one. So you start here, and you go counterclockwise. And then at B1 here, this is minus quadrant. So you can turn here. So you turn, and then you're not turning at B2, and you're not turning at B3, and you go back to A1. So basically, this is a bygone, right? So and the minus quadrant here, right? So, but this has no orientation sign, right? So when you take sign, you only look at the shadow. There's no shadow in here, so there's no minus sign. So this is plus B1, and then here you also have a plus B3. So you go here, and then you turn at B3 and go back. Here, plus B3. And the last one is the B1, B2, B3. So you have B1, B2, and then B3, and then go back. So this is the differential of A1. So differential of A2, I will not do it one at a time. I'll just give you the answer, and this is an exercise for you. So differential of A2 has 6 terms. Okay? So let me just point out that for A2, some of them is harder to find. For example, this one, B2, B3, T1. So what happened here was that you start with A2 and you go around, and then at the first time that you go through B1, you're not turning, right? So, and then the first time you turn, you actually have B2, and then B3, and then you go along, and then you actually go through this T1, and then come back, and then go here, and then not turning, and then go back to A2, right? So this is a disk that's like self-folded. It's a self-folded disk. That's also possible. Okay, so watch out for that. All right, so now let's talk about augmentation variety. So the link that A, B, C at 0 and trivial differential. Okay, so an augmentation is a DJ homomorphism from the Chekhov DJ to Chekhov-Yashva DJ to this trivial DGAC. Okay, so the augmentation variety is defined to be the moduli space augmentations. Okay. So note that so the augmentations
on the
yes.
On the previous slide, can you show what disk corresponds to term T1?
T1 here?
Oh?
Is this the one you? Is this the one
T2
you're looking
inverse,
at?
yeah, or T1 inverse. Yeah. Oh,
okay. Yes. Okay. All right. So augmentation is the augmentation variety is moduli space of the augmentations of the DGA. So know that what does augmentation do? Augmentation basically assigns complex numbers to degree 0 generators of your DGA, and then take the zeroth homology, and this is a commutative algebra, and then you just take the spec of that. So the spec of that is the augmentation variety. Okay. So now, example, partial A1 equals that, give coordinates B1, B2, B3, and C star squared with coordinates T1, T2. So T1, T coordinates of C cross, because they are invertible. These are two copies of C, and then you have, so it's a 5-dimensional affine ambient. Have two equations. You cut it out, you get three-dimensional affine variety. Move on to a symplectic field theory aspect of the Chekhov-Ilyashva DGA. So what you do, you take another copy of R, so with the coordinate T, and then you form the R4, and then define the symplectic form to be the exterior derivative of e to the t times alpha. So alpha was the contact 1 form. And you take the exterior derivative, it becomes a 2 form. It's a closed and non-degenerate. So this is called the symplectization of the standard contact R3. Okay, and then you also fix an almost complex structure on R4, so called J. Okay. So given any Lagrangian link lambda, you can actually take the cylinder of lambda, so by just doing the product with a copy of R. So this is an exact Lagrangian. Okay. So the exact means that the restriction of this one form, e to t times alpha, is an exact one form. Exterior derivative equals e to t times alpha. So any disk that we were looking at before, they actually turn into an R family of puncture disks. Right? So the of the original picture in the Lagrangian projection, if you turn them into the R4 picture, so that the corners becomes punctures at infinity. So you have a positive puncture at B and a bunch of negative punctures at C. So that's the picture of how you see the disk in R4, and these are J holomorphic. Okay. So what I mean by the R family, so the R family means that you can actually translate up and down, because you can, there's a copy of RT there, so you can translate the disk up and down in the T direction. So that's why you get an R family of that. Okay, all right. So instead of just a exact Lagrangian cylinder, you can also consider exact Lagrangian cobordism between links. So for example, this is a cobordism. So you have a link at some height, and then another link at some other height, and then you have exact Lagrangian surface that has boundary at those two parts. Right? So this is an exact Lagrangian cobordism. So Ekholm, Hunter, and Kalman had a contravariant takes this exact Lagrangian cobordism and spits out a DGA homomorphism. So what we did in this project, we enhanced such a construction to DGA that includes decorations. So actually, in order to define the actual DGA homomorphism, you have to enhance further. So before, the DGA had mark point decoration, but now they have curve decoration. So at the end, you have mark points, and then we also decorate the surface with mark curves, such that the curves are connected to the point at the two ends. Okay? So we replace the mark point T with mark curves P and enhance them into A lambda plus P and A lambda minus P. Okay? So the functor goes between these two DGAs. Okay? And then the map is computed as follows. So you take so for B in lambda plus, image of VL star, so you take tuples of recall in the lambda minus, and then take all cobordism, so we boundary on the cobordism, and with a puncture at D and a bunch of punctures at C, and then you compute the sign of the disk. So this is more complicated to explain. I will not explain it here. So the sign has something to do with decorations and spin structure. Mark curve, the boundary, and the mark curve. Okay, so you kind of start you. Okay, so so there are also natural DJ enhancement homomorphism. So the original DJ maps that goes from the original DJ to this enhanced version of DJ with curved right? So if you compose the functorial DGA homomorphism with this coefficient enhancement homomorphism, then you get the Chekhov-Eliashberg DGA to the enhanced version with Mark curve coefficient, and then you follow by this functorial DJ homomorphism to land at the A minus P. Okay, and then you can dualize this composition to get the morphism of augmentation varieties, right? So this is algebra, this is geometric space, so they are dual to each other. So if you dualize that, so that's why I dropped the upper star. So you get a map from the augmentation of lambda minus P to the augmentation of lambda plus. So you get that. So Ekholm, Hunter, Kalman, so this is a typo, I think. The A, this should be an accent on the A. They prove the following, and so by following the construction, it's a natural enhancement of their result. So if L and L prime are related by Hamiltonian isotopies, then the induced DGA homomorphism differ by a stable tame isomorphism. Okay? And then consequently, if your Chekhov-Eliashberg DGA are concentrated at non-negative degrees, then the induced augmentation variety morphism, they will be equal, right? So they will actually be equal morphisms. Okay? So that's their result, and it follows quite easily if you enhance to characteristic 0. So next, so let's talk about feelings. So a cobordism go from bottom up, right? So bottom is empty. So a cobordism from empty set to a link is called an exact Lagrangian feeling of the link, right? So you can see it fills it up, so it turns it into a surface. So Chen proved that an embedded exact Lagrangian feeling of a Lagrangian link has Euler's minus of that. And the feelings, embedded Lagrangian feelings, are actually topologically the same. They're just some sort of genus G surface with boundaries, right? But they're not the same under Hamiltonian isotopy. So really, you need to put into context with this category, right? So we're looking at Lagrangian stuff, we look at Lagrangian stuff. So the isotopy, you need to talk about the Hamiltonian isotopy. They're the one that generated by Hamiltonian flows. Okay. Right. So by the HK theorem, right, we can actually use the image of this composition to have of the empty set with the decoration coefficient to the original augmentation variety, and you can use this image to distinguish different feelings out. Right. So the question is that, are there any links? This is a question that has been posted long ago, and we have an answer in our project using cluster theory. So now let's move on to positive break closures. Just want to know, like, when should I stop? So this is the third part of the presentation, and I think I still have Misha. Okay. Anyways, let me continue that. So let's move on to positive braids. So what are positive braids? So basically, the semi group generated by a bunch of generators, right? So the same set of generators is a symmetric group, and then you subject to the Braid relation. So the good old Coxeter relation, And then, but you do not put in SI square equals identity. So the SIs are actually, so SI square is actually a new element, right? So it's just subject to the Braid relation. Okay. And any presentation of a positive braid is called a word, and its length is defined to be the length of the braid. All right, and given a word and a positive braid, you can draw the braid as an oriented tangle of n strands going from left to right, right? And then use the crossing of this form. And then if you can put in cusps, and then you can also put in parallel strands on top, you get a front projection of some Lagrangian link. For example, if you take 1, 1, 1 in a 2-strand braid like this, so you draw 3 1s at the bottom, and then you put in cups at the two end, and then you get this front projection. So it is actually a Lagrangian link. So we call this the Lagrangian link closure of the positive braid. Okay. So you can also use Eng's resolution to turn it into this picture. So basically, you replace the right by this small loop and smooth out of the left cusp, and then you get. So it's not easy. So let's do more. So for braid closures, unfortunately, there's a more systematic way of doing so. So what you do, so first you label the levels of the braid, right? So at the bottom, it go from 1 to n, and at the top, it go from n to 1. So depending on how many levels you have, you just label the levels 1 to n. And then you use matrix Mij to keep track of this between the ith level on top and the jth level at the bottom. Okay, so let's start. So at here, 1 and level 1 on top and level 1 at the bottom. So 1, 1 corner is a 1. There's no disk between 1, 2, and no disk between 2, 1. But then there's another disk between 2, 2. So you have an identity matrix at this point. And then next point, what you need to do is operation to the matrix, right? So for example, whatever disk you get here, you can compose with this piece to get a new disk between 1, 1. So you have this B1. So you turn at the B1 corner, so you have a B1 here. And then you have a 1 between the 1, 2 in the 1, 2 end, because whatever come from 1, 1 here, you can extend it into this disk. You have a 1 here. And then you also have a 1 here, because from 2, 2, you can continue into a 2, 1, and that's it, right? And then you move on, right? And then you just moving your matrix from left to right. So here just have another matrix of this form and another matrix of this form. And then at this pause, and let's compute the product, you get this product. And in particular, compute the power of A1. This is almost it, right? Because you know that A1 has one disk on the right-hand side with the T1 inverse. And on the left-hand side, it's just whatever you get from M11, right? So you just have the M11 here. This is the entry that you get. So you have T1 inverse plus B1 plus B3 plus B1, B2, B3. Sorry for the equal 0 here. So I think I get ahead of myself to put in the equation, cutting out the augmentation variety. So ignore this equal 0 for the moment. Right? So this T1 inverse plus M11. So what about partial A2? A2 is slightly harder, right? A2, or you have this part, right? So you can have this from this part. So you actually, you should be looked. So actually you can compute this M prime by first taking the 2, 2 entry of M, which gives you this kind of disk, and then you have to add in another term which takes in this that first go between 2 and 1, and then follow through at T1, and then you take in this from 1 to 2. So you have the M21, T1, M12. Right. So you compute the disk at this M prime point of the picture. Okay. And then and then you just expand it out, you get B2, T1, B2, B3, T1, T1, B1, B2, and B2, B1, B1, B2. And then this is almost partial of A2, except there's another T inverse on the right. So you get T2, partial A2 is T2 inverse plus this whole quantity, and exactly 6 terms. Okay, and also get ahead of myself and putting an equal 0 there, so ignore that. Okay, all right. So next, if you want to consider, yeah, so this is the when the 0 comes in. So next, if you want to consider the augmentation variety, you just set those to be 0. Okay? So and T1 inverse equals minus, T1 inverse equals minus M1, and also T2 inverse equals M prime. So we have that. And then since T1 inverse is non-zero, you can actually multiply the second by 1 inverse, right? So what you get so you take the prime and put it here, so you get minus M11 times minus, so it was minus M here, right? So you have a minus M22 minus M21 times M2, I think 1 M12, there's a typo. Right. So this is exactly the determinant of this matrix M. Okay, so the first equation is that this entry is non-zero, and second equation is that this whole matrix has non-zero determinant. So in general, this is true. So if you take a braid wood that's I1 to IL of n-strand braid, then you can first compute the discounting matrix of this form. So what you do is you put in this B110 block inside a matrix and call it Z sub I. So the I tells you which block you put in. So it's the I comma I plus 1 block. And then you just do this matrix modification. So at the end, you get a n by n matrix. And then the augmentation variety is cut out by the non-vanishing locus of the product of the principal mothers of this matrix. So basically, the first entry has to be non-zero, and then the 2 by 2 corner is non-zero, the 3 by 3, the determinant of the 2 by 2 corner, and the determinant of 3 by 3 corner, and the determinant of this, they all have to be non-zero. So that's why you can just multiply all of them together and then take the non-vanishing locus inside this affine space. Right. So note that non-vanishing locus of a single polynomial is smooth. So we know that the augmentation variety of this positive braid closure is a smooth variety. Okay. And also we know that this non-vanishing locus condition looks a lot like the defining equation earlier work between me and Lin Hui. And so let's now move review of the double polymers in cells. Okay. So the general construction in Peterson group G, right? So if you just consider today's presentation, you can let G be just SLN. Okay. So in general, you can let G be any Peterson group with a pair of opposite barrels, and then all the left coset of the positive barrel as B with subscript, and left coset of B minus as B with a lower subscript, with a subscript. Okay, and relatively 3 of them. So depending on the subscript. So if you take both plus, and you have the XB plus W if I is in cell, and then you have the same thing for minus. So this is what's called a Tits distance, and you also have a Tits co-distance. So if you take a coset of the minus and a coset of the plus, then you can just draw a line and then lay something, and you do so if X inverse times Y is inside this Birkhoff cell, B minus WB plus. Okay, and in particular, if if this is the identity element in the Y group, then we just ignore it. You just drop it. Just draw a single line, and that's the general position condition. So this is a co-distance. So the shorter the Y group element is, the farther away these 2 cosets are. Okay. So definition cell is the following. So you first pick positive braids, fix a pair of positive braids of G, right? So in general, for general G, you have general braid lines. So the braids are determined by the coordinator of the group. And you take words of beta and gamma. So you have I1 to IL, you have J1 to JL, right? And then the Bell-Samuelson cell is the configuration space of the following shape. So you have the plus cosine and the minus cosine on top. So for convenient paper, the plus cosine on top, but now I put identity at the top and the positive braid beta at the bottom, like this, right? Then you can first use the G action to turn the left edge to be U minus and B plus. And then since B1 is SI away from B plus, you can just parameterize it with R sub I1 Q1. And then you keep doing this, right? So you R sub I1 Q1, R sub I2 Q2, B plus, and so on and so forth. At the end, you get R sub I1 Q1 all the way to R sub IL QL B plus. Right? So you have this. And then you remember that we also have a general position condition on the right. So that requires that all the minors of this product of matrices has to be non-vanishing. Right? So the double Bell-Samuelson cell is the non-vanishing locus of the matrix, the minus of the matrix that's the product of all the R sub I Qs. Okay? So this looks a lot like what we had earlier for augmentation variety. Okay? So indeed, right, when G is SLN, this R sub IX and Z sub IX only differ by a sign at the I comma I plus 1 entry. Okay? So to compensate for this sign difference, right? So we called it the diagonal matrix. We introduced something called a Sine Matrix. So any diagonal matrix with diagonal entries plus minus 1, they're called Sine matrices. So basically, it's a diagonal matrix. It's just plus minus 1 along the diagonal. Okay. So there's actually a right semi-group action on the Sine matrices defined by the following. So you can add by this generator. So what it does is keeps all the entries the same except at the I plus 1 entry. So you switch them and then you put a minus sign at the I plus 1 entry. Okay. So you switch the I and the I plus 1 entry and then you change the sign of the I plus 1 entry by a minus sign. So that's what it does. Okay. So you can prove that this is actually a semi-group action on Sine matrices. Okay. And you can also prove that Z sub IX is actually equal to, for any Sine matrix C times R sub I times this Sine matrix evaluated at this the simple root alpha I. So alpha I basically pulls out the I and the I plus 1 entry and then multiply them together. Right. So C to the alpha I times X. And then you multiply by another matrix that's a result from acting on C by SI. So this identity always holds. Okay. So now if you have a Sine matrix C, you fix a Sine matrix C, and then you fix a word for beta. So you let C0 be C itself, and then let CK be the result of acting on the right by a subword, right? So from I1 all the way to IK. So this is a positive braid, you act on C by this, and then you define epsilon K to be the sign of this CK to the alpha IK minus 1. Okay. So this epsilon K is either plus 1 or minus 1, basically. Right. So now you can do the following computation. So this product of Z sub I, you can turn it into a product of Sine matrices with these R matrices. So you have this, and then you can use the fact that Sine matrices are self-inverting, right? So they are all, the entries are all plus minus 1. So you multiply them together, you multiply it to itself, then you get identity. So this cancel. So you end up with this. Right? So that's how you translate between the Z matrix and the R matrix product. You have that. Okay. All right. So this is our first theorem. So finally we get to our theorem. So our first theorem is this following. So for any choice of Sine matrix C and any word, right? So you can define CK and epsilon K as previous. Then you can define an isomorphism between the ambient space, right? So these are two affine spaces. So you pull back Q to be epsilon k bk. So this isomorphism between ambient space restricts to a biregular isomorphism between augmentation variety and the double Bose-Emerson cells. And this biregular isomorphism does not depend on the choice of word. Okay? However, it does depend on the choice of the Sine matrix. Okay? So following the same recipe as in our work on the double Bose-Emerson cells, we show that this version of double Bose-Emerson cell is also a cluster K2 variety, also known as a cluster A variety. So therefore, the biregular isomorphism induces a cluster K2 structure on the augmentation variety. Okay. However, this induced cluster K2 structure depends on the choice of Sine matrix. Depends on what Sine matrix you use as an input. But this is not the bad news. Too much of bad news. The good news is that the dependence is really weak. Right? If you change the choice of Sine matrix, you only change the cluster variables by a sign. Okay? The cluster charts and the quivers remains unchanged. So this is really important. Right? So somehow this is like a weaker version of cluster structure. Right? The variables are up to sign, but the charts, namely the torus, algebraic torus inside the variety and the quiver, they are unchanged. Okay? All right, and moreover, there's a connection between these cluster charts and the family of exact Lagrangian feelings. Okay. All right, so now we move on to the final part of our presentation, feelings and clusters. Okay, so let me first introduce pinching. So what is a pinching? So pinching is that it's locally a saddle cobordism. So what you do is you take a parallel strand in the front projection and then you pinched it. Right? So you can see from this picture here. So in front projection, it looks like a pinch. Right? In the Lagrangian projection, it looks like a resolution of crossing. So you have a crossing and then resolve the crossing. Okay? So in the 4D picture, it looks like this. It looks like a saddle of this form. Okay? And then for positive Braid closure, lambda beta, all degree 0 ripcords are contractible, pinchable. Right? So you can do this operation to any degree 0 ripcord. So if you rotate this picture 90 degrees counterclockwise, you get this picture. So this is exactly what happens when pinching a degree 0 crossing. So this is a crossing in the braid. You pinch it, they become a parallel. Right? So from this we see that pinching degree 0 ripcord results in another positive Braid closure. Okay, so we actually developed in the project. We developed a way to compute this functorial augmentation variety cobordism using some sort of matrix scanning technique. Right, so it's too complicated to present it here. It's similar to what we did when we compute a partial of degree 1 ripcords. Right, so it's a similar technique. Right, so we actually can use that to compute the cobordism homomorphism as well. Okay, and so so now let's talk about pinching sequence. So now if you have a braid of length L, right, you can take any permutation sigma in SL, and then we can pinch the crossings one by one in the order according to the permutation. Okay, and then resulting link after the pinching, right? So you pinch all of the braid crossings. At the end, you get a disjoint union of n copies of the maximal TB are not, right? So you have n copies, and then you can fill them up using this minimum cobordism. Right? So for each maximal TB are not, you can just fill them up. So the composition of all this gives you an exact Lagrangian feeling, which I denote by L sub I sigma from the empty set to the positive Braid closure. So the next theorem that we prove that is the following. So first, this augmentation of the empty set with declaration is it's actually an algebraic torus that's of rank L. Okay, L is the length of the braid. And then the functorial morphism from this to the augmentation variety is an open embedding. Okay? And now we are embedding an algebraic torus into a cluster variety. And then the good news is that the image is actually a cluster chart inside a cluster variety. Okay? So that's another theorem that we proved. Okay? All right, so let's actually do an example. So let's take the 111 braid. Right, so the closure is actually the trefoil. So believe it or not, this is a trefoil. right? And then let's take the permutation 1, 2. So this is a cycle notation. So basically 1 goes to 2, 2 goes to 1, and then 3 stays self. So the first, so according to this permutation, the first thing we want to pinch is 2. So let's do that. So we pinch 2, right? We get this picture, okay? So you get a pair of pants here, like that. Right? So now B2 is gone. Oh, by the way, so why do I have the B plus and minus there? So because each crossing is actually a double point, so I denote the upper point as plus and the lower point as minus. And then this is a knot. So topologically, it's just a circle. And if you go around the circle, you actually encounter the points and the mark points in this order. So that's how I recall this mark point and the ripcords. So you pinch B2, you get this, right? So now it becomes a 2-component link. And then if you go around each component, you see the the mark points and the ripcords in this way, right? So this is what you get from the functorial homomorphism. So this is a black box in this presentation, but just believe me that this is what you get from the computation. And then you pinch it again at 1, right? So the B1 is gone, and now you have you back to a single component link. Okay. So the blue curves here are the mark curves, right? So they are the ones that give rise to the variables, the coefficient formal variables. Okay. So you have that, and then you pinch it again, you get again a 2-component link. Actually, so each component now is an unknot, right? So you see that you actually get 2 unknots here. Okay, and all the ripcords are gone, and you get this. You end up at this homomorphism image. So the ripcords are now mapped to these Markov coefficients, and then at the end you fill them up with minimal cobordism. So basically, you just fill up the 2 circles. So you see that this is a filling, and this is actually a 1-puncture torus filling up a circle. Okay? And then the last step will give you 2 conditions: P1, P2, P3, T1 equals -1. So the product of these mark points is -1, and the product of these mark points are -1. Okay. So there's a way to fix this condition so that the product is +1 by incorporating spin structures, but I'm not going to do it in the presentation. So a more prettier version is they multiply to 1 if you take into spin structures and take spin structure into account. Okay, right. So now I think I'm almost out with my time. So let me just point out that what the cluster variables are in this case, right? So let me also talk about it. So the augmentation of the empty set with the Markov coordinates coefficients. This is a torus of rank 3 with coordinates P1, P2, and P3. So these are invertible variables. So they are coordinates of this torus. So the embedding maps into the augmentation of 1, 1, 1 inside B1, B2, B3 in C3, and the pullback map is given here. Right? So this is actually the pullback map. Okay. Right. So the Lagrangian for augmentation variety is cut out by from this space by this equation. Right. So beginning we saw that there are 2 equations, but actually they are the same equation. Well, they give you the same locus if you ignore the T2. So you get this. There's 5 clusters. So let me start with the first one. So the first one, the one that we had in our earlier picture, is this one. So so if you take the variables B2 and then minus B1, B2 minus 1, and then T1. So the blue one is the frozen one. And then if you plug whatever you get here into these formulas, then you see that this is actually P2, this is minus P1, P2, and this is minus P1, P2, P3. Right? And since this tells you that this is indeed an embedding of torus into the cluster onto the cluster chart. Right? So this is an isomorphism between tori. Okay, and why do I have a plus minus sign here? Well, because earlier we said that it really depends on the Sine Matrix choice. So when you define a cluster structure, you just choose a Sine Matrix. So the Sine Matrix can change this sign. So it's either a minus sign with a plus sign here or a plus sign with a minus sign here. So there are 2 choices in this case. Okay, and here are the 5 clusters. So you have So if you mutate, you get exactly this many. And if you recall, you have this braid is of length 3. So the permutation group has 6 permutations. So what happened? Why do you have only 5 clusters? Well, this cluster actually corresponds to these 2 permutations. So both of these permutations give you the same cluster, give you the same feeling. Right? So you have these 5, and it is indeed the A2 cluster variety with 1 frozen variable. Okay, so there's also a way to draw the initial seed. Right? So this is basically following the amalgamation process. So I'll be really quick. So just draw the braid, put the vertex in each face. Oh, by the way, so what I'm drawing here is the initial seed corresponding to the identity permutation. Right? So therefore, for the other permutations, we have an algorithm of computing the result from the identity one. So we just describe how you do the identity one. So you put a vertex in each face, and then you draw this kind of triangular pattern between the vertices. Right? So you finish it, and then the dash arrows are half weighted. So most of them cancel out. Okay, so we end up with this. And then you just simply delete the left vertices. So you delete them along with any arrows that are incident to them. So this is the quiver you get. So this is the quiver you get. And in particular, this is an infinite type acyclic quiver. So I think I ran out of time, but at the end we'll use this. So let me just quickly go to the result. So this is so you can actually do a rotation action on this braid by moving the first crossing to the last one. So it's a bunch of Breidemeister 2. Okay. And then blah, blah, blah. So this is related to the DT transformation. So the important theorem is the following. So for any Sine matrix and any positive braid, you just define the Sine matrix you just take the result of acting on C by beta, and then we have the following commutative diagram. Right? So you have the square root of the Donaldson-Thomas transformation at the bottom, and then you have this rotation on top, and they commute. Right? So using this, and if your DT is of infinite order, then we can actually distinguish. You can actually construct infinitely many non-Hamiltonian isotopic feelings. So this answers our earlier question. So if your DT is of infinite order, and then the positive braid closure emits infinitely many non-Hamiltonian isotopic exact Lagrangian feelings. Okay. And then a work by Lee, Mills, Schiffler, and I forgot the last person. Then we know that there's a necessarily sufficient condition if your quiver is acyclic, right? So it's of infinite order if and only if the quiver is infinite type, right? So then if somehow you know that your augmentation variety, the underlying quiver is acyclic, then and of infinite type, then it always emit infinitely many non-Hamiltonian isotopic exact Lagrangian feelings. In particular, this applies to the earlier example that we saw, that's an acyclic quiver, and it's also of infinite type. So that Legendrian link would have infinitely many non-Hamiltonian isotopic exact Lagrangian feelings. Okay, so yeah, so now I will end with a bunch of open questions that I don't have time to go over, and thank you.
Hello.
Yeah, sorry for going over time.
I have problem with connection, so any questions for Daping?
Do you think there's any chance of classifying when DT has infinite order?
Well, for acyclic quiver, the collaboration between Lee and
that's kind of a special situation.
Right, that's a special situation. Yes, you're right. Right. So in general, we don't know. So in the double box Emerson cell paper we did with Lin Hui, we talked about finite order of DT. So we know that at some point, for some cases, DT is finite order. but
Yes.
it's hard to tell when they are of infinite order. In fact, we believe that often they are of infinite order, but we don't know how to prove it.
Yes.
Right.
Any other questions? I have some. Daping, I kind of get lost in the middle and disconnected so several times. Can you, I don't know if you tell it or not. So can you explain how augmentation variety is related to feelings? So can you say?
Right.
Yeah.
Yes. Let me go back to the theorem that's about that. Right. This theorem. So so for this kind of feeling that we constructed by pinching.
Yeah.
Right. So we know that the resulting augmentation variety of the empty set with the decorations and algebraic torus. Okay. And then the functorial morphism from this cobordism gives you an embedding of torus into the augmentation variety. And the image of this embedding is exactly a cluster chart.
Okay.
Right.
So different cluster charts correspond to different feelings.
Yes.
Okay.
Well. So a subset of the cluster charts. So in general, there could be infinitely many cluster charts. Right. Many cluster charts that we don't know whether they're corresponding to feelings or not. Right. So we only know, and also there could be other feelings that we don't know whether they correspond to cluster charts or not. So this is actually one of the open questions I think that I wrote down here. Right. So we only know the correspondence between a subset of feelings and a subset of cluster charts. So I think it's this one. So can we extend the connection between feelings and charts to a bigger family? So this is also a question.
And for example, if you have some information, yeah, so your cluster variety is just variety over C, right? So it's kind of,
yes.
This Richard Samuelson variety over C, right? Yeah,
Boss
so
Samuelson.
if we know any information about topology of this variety, does it give you any information about feeling?
So we know that it's smooth.
Yeah, but say, I don't know, say pi1 of this or something like that. So you know some topological information about this augmentation variety. Do you know, well, does it give you any information about feelings or something?
If you know that there's some pi1 in it.
Well, I don't know if it's pi1 or something, some topological kind of invariant of.
I'm not sure. I'm not sure because so feelings correspond to charts. Well, ideally speaking, right, they correspond to charts. But I don't know like how you relate.
But you say not all charts, but some charts, some specific charts.
Right. But even suppose that we know that they all correspond to charts. Even that we don't know like how you translate between.
Okay.
Right. Yeah.
Your charts depend on two pieces of data, a reduced word, and also the sequence in which you pinch.
Yes.
So presumably they're connected by mutations. What is the combinatorics of, I mean, you can do Braid moves to the reduced word, and also you can change the permutation. Which of those corresponds to mutations?
Well, so both of them should correspond to mutations. However, it is unclear. So I think this is the first open question here. So we have an algorithm of computing this cluster chart starting from the word and the identity permutation, right? But then this algorithm is actually not very efficient, right? So actually it gives you a long mutation sequence, right? So if you just hand me some word with some permutation and then just change the permutation by a little bit and then ask like what's the relation between the two charts. So it turns out that the mutation you need is sometimes it's more than one or two. So we actually have an example that needs 3 mutations to get from one to the other, even if you just change it by a simple transposition. On the other hand, if you change the word, it's relatively easier. If you change the word, I think this is so from the double box Samuelson cell paper, we know that it's a single mutation. So if you change the word by some Braid move, it's a single mutation. But if you change the permutation, then it's vastly different. And I don't know the answer. It's also an open question.
Thanks.
Thanks, Daping. So let's thank Daping again. And I apologize. I don't know about the quality of recordings that I tried to make, so it might be disaster. But anyway, so could I ask you to send me your slides, so I will post it on this webinar webpage?
Sure.
Thank you.
Yes.
And by that we conclude this how it's called spring session of our seminar, online seminar. So I hope to well, we can continue it in fall. Okay, thanks everybody, and
thank you, organizers.
Thanks, Leonie, for organizing.
No. That's for you.
Organizers.
Yeah. Okay. So, bye-bye. Thanks.